Okay, with our second day on 8.2, we're going to revisit some problems that we did yesterday. We're going to eventually integrate with respect to y instead of integrating with respect to x. Look at the notes here. Yesterday we did this problem. Actually, we had problems kind of like this on our homework. Find the area of the region in the first quadrant. So we're only here in the first quadrant. Bounded above by y equals square root of x. That's actually half of a sideways parabola. So above, we have this boundary. Below, it says we have the x-axis and the line y equals x minus 2. Now the line y equals x minus 2 has a y-intercept of negative 2. And we have a slope of 1. So you can see relatively quickly that our line would cross uh, the radical function, the square root function, obviously somewhere in that first quadrant. But please watch out. The area is completely enclosed in the first quadrant. So that's where that x-axis part is coming into play. The lower boundary is the x-axis and then the line coming up over here. Now clearly on this leftmost edge we have 0, 0, the origin. This bottom x-intercept of the line here, if you set y equals x minus 2, if you let y equal 0, you'd quickly see that x would equal 2. You might even wonder what point of intersection we have. You could set your two curves equal to each other. You could set y equals radical x equal to y equals x minus 2. And certainly you could solve and find where those two curves cross each other. I do want to say this much, though. You can solve by inspection. Looking at this radical, you might wonder if there might be a friendly point. A lot of times that is the case. If you think, what are some common square roots that we know? Maybe the simplest, other than 1, would be the square root of 4. And if I were to let x equal 4, the square root of 4 would be 2. Now on the right side, if I let x equal 4, 4 minus 2 is 2 also. So that would mean that x equals 4 would solve this equation. And of course, if you were to plug x equals 4 into either one of those two curves, you'd get y equals 2. Now I bring this up just to remind you that we need boundaries, we need limits as we integrate. And we're going to set up an integral, or actually we're going to have to set up two integrals. We talked about how you always have top minus bottom, but I want to point something out to you. We looked at a problem like this yesterday. As you are closely looking at this region, you're going to notice, I hope, that the bottom boundary in green here is the x-axis. The top boundary is still radical x. When you move over to the rest of this region, just disclosed in yellow, represented by yellow, you'd see that the top boundary is still radical x, but the lower bottom boundary has changed. It's no longer the x-axis. It's the line y equals x minus 2. And by the way, that's what this wording is really warning us about. The fact that they're even saying down below, you're going to change boundaries. So how do we compensate? Well, we'd have to break this up into two distinct integrals. We'd integrate from x equals 0 to x equals 2. We're talking about the green region right now. And we'd take our top boundary, which is radical x. The bottom boundary is the x-axis, and the x-axis is actually y equals 0, the line y equals 0. And then we'd have dx. By the way, this is the type of integrating that we were doing earlier in the year when we were always integrating from a curve to the x-axis. But now we're going to say add to that the region that we have in yellow. We're going to go from x equals 2 right here to x equals 4. That's where we'd be building our rectangle, so to speak. And again, we're going to do top minus bottom. Well, the top would be radical x again. But what about the bottom? Now that bottom is x minus 2, y equals x minus 2. And we could work this all out. This problem would be challenging because we need two integrals as the lower boundary has changed. So anytime you have an upper or a lower boundary changing, that's problematic. And if you can avoid that, of course, we would like to. So today we will learn a new way of solving area problems that make complex problems easier. It sure would be great if we didn't have to write two distinct integrals. So this method involves integrating with respect to y. The setup is going to be as follows. We're going to, of course, have a dy instead of a dx. We're always going to have a right minus left kind of a connotation. No longer top minus bottom, but a right minus left. We're going to have our first y value and our last y value up here. So we'll have numbers, but they will be y values. And then, of course, what you're really going to do is have different forms inside the integral. If we're working with respect to y, we need equations of the form no longer of y equals something, but x equals certain functions with respect to y. So, my goodness, we need to revisit this problem right here and see if we could perhaps get a little bit of help. Just redrawing this picture super fast that we just had, we had y is equal to radical x. But you know what? We'd really like to see if x could be thought of as an equation. How about we square both sides, and then we could say that x would equal y squared. Square the left side, square the right side, and then I just switched. So why am I writing it like this? Well, now I could at least have an alternate form here. So we also are going to have this other scenario where we had the line was y was equal to x minus 2. Well, in a perfect world, I'd like to see x equals something. I could have x equals y plus 2. So this lower boundary right here, I'm going to say x equals y plus 2. How would that help? Well, it would help tremendously because right now as I'm looking at this yellow region, if I were no longer looking at a top minus bottom connotation, if I were building rectangles going in a vertically stacked kind of a setup, I could always have a right minus left connotation, and the right and left boundaries wouldn't change. That's the biggest thing that you'd need to see, the right and the left boundaries. The right boundary for any rectangle that you could draw here would always be the line x equals y plus 2. The left boundary of this little rectangle would be x equals y squared. So that could be extremely helpful. And using this setup right now, I'm going to feed in and say maybe we could set up this problem. I'm going to go from my lowest y value, which happens to be 0. What about my highest y value? The highest y value I hope you can see is 2. Look at the top intersection point. It's 4, 2, but I'm going to write the y coordinate. I'm integrating with respect to y. Now what? Well, I'd like to say right minus left. But I'd like to have x equals equations. The right boundary was x equals y plus 2. How about the left boundary? Well, the left boundary was x equals y squared. And at that point, you can now do this problem. It would be equivalent to working the problem out if you wanted to break it up into two integrals and do it with respect to x. This being said, let's go ahead and see if we could finish this. Minus a y squared, if you'd like to bring a minus y squared out in front, you certainly may. Just finishing this problem up, let's quickly use our fundamental theorem. Bump our power up 1 and divide by that new power. Here we'd get y squared all over 2, and this would be 2y. And I'm going to evaluate that between 2 and 0. Well, finishing this off, we could say negative 2 to the third all over 3 plus 2 squared all over 2 plus 2 times 2. And then we could say subtract. Well, thank goodness, when you plug a 0 in to those three expressions, you're just going to get zeros clear across. That's probably the nicest part of the problem. Well, continuing, I'm running out of space over here. We'd get negative 8 thirds. Here's 4 all over 2 is just a 2, and 2 times 2 is 4. So this is actually 6, 4 plus 2 plus negative 8 thirds. But 6 is really 18 thirds, if you think about that. Negative 8 thirds plus 18 thirds is 10 thirds. So that is how you would do a problem more quickly. You don't have to break that up into two distinct integrals. You just have to change your way of thinking just a little bit. All right, so what I'd like to do right now, I'm afraid we're going to have to go to a second video to finish this problem. But let's just get the problem started first of all. If we would just graph y equals x cubed, and I'll make that right down the middle here. Y equals x cubed, of course, is looking like this function right here. And you might, in this problem, perhaps want to think of this problem in terms of x equals a number. I hope that it wouldn't be too much of a jump for you to take a cube root on both sides and see that x is equal to the cube root of y. We could certainly do that. This other equation, though, x equals y squared minus 2, definitely want to talk to you about that. A lot of times kids look at the y squared aspect and they will correctly guess that this is going to be a parabola. And it is. It's going to be a sideways parabola. It's a sideways parabola with positive y squared. I hope you might guess it's going to open to the right. But so very often kids will say, well, now the minus 2 is confusing me. I don't know if the sideways parabola would be over here or if it would be 2 steps to the left of the origin. Sometimes kids even wonder if it might be moved up or down 2 steps. Well, maybe to help you out, the x-axis is the line y equals 0, and if you let y equals 0, very quickly you'd get x equals 0 squared minus 2. You'd get x equals negative 2. It looks like we're going to have this curve on that 2 steps shifted left. So definitely want to talk to you about the importance of being able to determine what a graph looks like. You could also solve for y if you'd like. You could add a 2 to both sides. If you were solving for y, you'd have to take 2 square roots, a plus minus radical x plus 2. Regardless of how you're setting it up, I hope you see an enclosed region right here. And we're going to run out of time in just a moment, and we're going to pick up and determine whether this problem might be more easily done integrating with respect to x or with respect to y.